Yeah, so now we have Yellow talking about entanglement suppression, emergent symmetries, and a standard model like Higgs boson. Thanks.
Okay, thanks to the organizers for the opportunity to come back here. This is going to be a very different talk from all the talks that we've heard today. First of all, I'm not going to talk about Bell inequality. Okay. Second of all, I would also not talk about any collider measurements, even though in the end I hope that I can make a connection to the collider measurement in the near future. But however, I want to hopefully convince you that the kind of question I want to talk about today cuts into the very core of who we are as particle physicists. That is about the way we talk about symmetry. So it's going to be, this talk is going to be about entanglement suppression, emergent symmetry, and a standard model like Higgs boson, which I believe a lot of our experimental colleagues care about. Okay, so it's not that separate from collider after all. All right, so I guess I don't have to explain to this crowd, what is entanglement. So basically, it just says that, for example, if we have a bipartite system, if the state vector cannot be written as a tensor product state, then it's entangled. But on the other hand, symmetry is also among the most fundamental principles in physics. It's a very powerful characterization of nature based on invariance under a specified group of transformations. And symmetries give rise to conserved quantities, energy momentum, angular momentum, etc. And when combined symmetry with quantum mechanics, there is a subtle realization of symmetry that is a spontaneous symmetry breaking. And moreover, all known fundamental interactions are based on symmetry principle. But what is the origin of symmetry? Okay, what is the origin of symmetry? And there are two historic perspectives. The first one is what I call the beauty in, garbage out perspective, meaning that the theory at the very high energy is very symmetric, has a lot of symmetry. But when we go to the low energy, the symmetries are all badly broken. So we see something very messy in the low energy. So we have beauty in the high energy, we have garbage out in the low energy. Okay. And the opposite perspective is what I call garbage in, beauty out, meaning that at very high energy, there is no symmetry at all, everything is messy. But somehow, symmetry emerges at long distances in the infrared. These are the emergent symmetries. And the most well-known example is the emergence of scaling symmetry at the renormalization group fixed point. It's an emergent symmetry, not present in the fundamental theory of our nature. But neither explain whether symmetry can be the natural outgrowth of more fundamental principles. Okay, we always take symmetry as input or as an accident. And we never have the handle or to ask, can symmetry be the natural outgrowth of more fundamental principles? And John Wheeler famously coined the phrase "if from qubit," meaning that if all things physical are information theoretic in origin. Therefore, it's natural to ask, can symmetry come from qubit? Or can symmetry have an information theoretic origin? Okay, so that is really the question I'm trying to study today. And so, as I said, and of course, we've heard many remarkable connections between fundamental physics and information science in the past decade. So it's very natural to ask, can symmetry come from qubit? Okay. So it turns out that the way I got into this is from a very fascinating paper in 2018 by a bunch of what you can call them nuclear physicists from Seattle with the title Entanglement Suppression and Emergent Symmetries of Strong Interaction. Basically, they claim that entanglement suppression in the strong interaction S matrix is shown to correlate it with approximate spin flavor symmetries that are observed in Lorentz baryon interaction. So this raises the intriguing possibility of understanding symmetry from quantum entanglement. So in this talk, I will try to understand emergent symmetry, global symmetries in two very different physical systems, Lorentz QCD, which is a non-relativistic system, and two Higgs doublet models, which is a fully relativistic system. And I want to find the connection between emergent symmetries and entanglement suppression in 2-to-2 scattering of particles. For example, in Lorentz QCD, it will be the 2-to-2 scattering of baryons or neutrons with protons, or in the 2 Higgs doublet model, that will be the 2-to-2 scattering of Higgs bosons. And I will try to elucidate the connection between the entanglement, suppression, and symmetry from an information theoretic viewpoint. And in the case of 2HDM, it turns out that a standard model Higgs boson emerges as an outcome of entanglement suppression. Okay, so that's sort of the grand plan today. And so let me first give you some sort of discussion about what are the emergent symmetries in Lorentz QCD. Basically, there are two types of emergent symmetry in Lorentz QCD. First is what is called the Schrodinger symmetry. This is the largest symmetry group preserved by Schrodinger equation. And this is also known as non-relativistic conformal invariance because it contains a Galilean boost, scale, and spatial conformal transformation. And another type of emergent symmetries in Lorentz QCD are the spin flavor symmetries. These are the symmetries which mixes flavor, an internal degree of freedom, with spin, which is a space-time degree of freedom. And this is possible only in non-relativistic systems. And the example of such spin flavor symmetry is this SU2NF, where NF is the number of quark flavor. There's an SU2NF quark spin flavor symmetry, and there's also Wigner's supermultiplet SU4 spin flavor symmetry that acts on neutron and proton. And so at the quark level, the spin flavor symmetries are known for a long time because these are symmetries of the non-relativistic quark model. So what you do is when you have in the two flavor case, you take the up and down quark, and their two spin states, you assemble them into a 4-dimensional vector. Okay, and then the system, the non-relativistic quark model is invariant under an SU4 rotation, mixing these flavor and spin. And the same thing here for 3 flavor, you have up-down strange with a 2-spin system. You assemble them into a 6-dimensional vector, and there is an SU6 rotation mixing the flavor and the spin. And it turns out that these quark level spin flavor symmetry can be derived from QCD in the large NC limit. And however, in Lorentz nuclear physics, there's a different SU4, first observed by Eugene Wigner back in 1936. This is even before we knew about quarks. So in this case, what Wigner observed is that if you take neutron and proton and their 2 spin states assemble into a 4-dimensional supermultiplet, then Lorentz nuclear physics is approximately invariant under SU4 rotation, mixing the proton, neutron, and their different spin states. Okay? And in the modern perspective, in the EFD language, the Wigner's SU4 is accidental in the sense that once I impose the SU4 quark spin flavor symmetry, the only remaining operator at the leading order has this Wigner's SU4. In this sense, it's accidental. And so far, these spin flavor symmetry can be argued from the large NC limit, but there are emergent symmetries beyond the large NC limit. And this has to do with a very particular feature of low energy nucleon-nucleon scattering. If you do the non-relativistic low energy nucleon-nucleon scattering, it's dominated by the S wave because you go to the very low energy and only contact interactions are important. So the scattering is in the S wave. In this case, the scattering is a 2-channel process that includes a 1s0, that is when the total spin of the 2-nucleon system is 0, and that's a spin singlet, or 3s1, that's when the total spin of the system is 1, and therefore it's a triplet. And it turns out that the scattering length okay, in this non-relativistic system, and again, just a very quick refresher that the scattering length describes the range of interaction when two particles collide. So for example, in the quantum mechanics, you learn that the total cross-section is given by 4 pi times the scattering length. So the scattering length tells you the effective range of the interaction. So it turns out that for the neutron proton scattering, the scattering length in both 1s0 and 3s1 are very large, are much larger than we naively expect. In NN scattering, say in the 1s0 channel, the scattering length is minus 23 Fermi, and 3s1 is 5.4 Fermi, and this has to do with the presence of a deuteron, which is a near threshold bound state. And in low-range QCD, everything is set by the pion mass. And 1 over n pi is only 1.4 Fermi. So both scattering lengths are anomalously large than 1 over n pi, which, the range of pion exchange is set by, is only 1.4, but the range of interaction in the NN scattering is much larger than that. Okay, this is just the typical binding energy. That's why the deuteron is very shallow bound state. And so in this case, we can take the limit, go to the limit where the scattering length A goes to infinity, because it's much larger than what we naively expect. And in this case, the system has no scale and therefore exhibit Schrodinger symmetry. It exhibits Schrodinger symmetry because this is a non-relativistic system. Everything is dictated by Schrodinger equation. And if you add scale invariance to it, this gives you the so-called Schrodinger symmetry. And so NN scattering has approximate Schrodinger symmetry that is not in the fundamental QCD Lagrangian. The question is who ordered that? That's one example. Another example has to do with considering the fact that nucleons are just part of spin 1/2 octet baryons. So in the SU3 flavor symmetric limit, we can write the octet baryon into a 3x3 matrix. And again, in the very low energy below the pion production threshold, we can write down the leading order operator that respect the SU3 flavor. Savage and Wise wrote down the leading order effective Lagrangian in 1995. There are 6 of them. The bracket here refers to the trace over the matrices. So there are 4 single trace operators and 2 double trace operators at the leading order. Okay? And so these coefficients C1 through C6, we can't calculate them because we don't know how to solve QCD. So our lattice colleagues actually simulated these 6 Wilson coefficients numerically under some very special circumstances. For example, this is one simulation of C1 through C6 for a very unrealistic pion mass. And you see the pattern is very striking that all C's are consistent with 0 except C5. So then there is an updated lattice simulation with a more realistic M pi. Again, you see the pattern here is all C's are consistent with 0 except C5. So you go to the effective Lagrangian and set all the C to 0 except for C5. It's a double trace operator. It turns out that I can rewrite this double trace operator in terms of this vector that is a 16-dimensional vector if I collect the 8 baryons and there are 2 spin states, so there are 16 of them, into a 16-dimensional vector. C5 is just B dagger B whole thing squared. This means that C5 has a very large SU16 spin flavor symmetry. Okay, again, it's a very large spin flavor symmetry that is not present in the fundamental QCD Lagrangian. And it's not a consequence of a large NC. So where does it come from? So just to very quickly, we talk about the quark spin flavor symmetry. We talk about Wigner spin flavor symmetry. These can come from large NC. But there's a Schrodinger symmetry. We don't know where it comes from. There's a SU16 spin flavor symmetry. Again, we don't know where it's come from. So our goal is to understand these 2 emergent symmetries from a quantum information theoretic perspective. Okay. And so to discuss entanglement suppression, we need to quantify the amount of entanglement. So again, I think for this audience, I don't need to dwell on this aspect, usually we use von Neumann entropy or we use linear entropy, but for a two-qubit system, they're all related. It all boils down to concurrence. Okay, everything is related to concurrence. So it doesn't matter which one we use, but usually linear entropy is easier to use because it doesn't involve the log. And so, but however, I want to emphasize is that entanglement is a property of a quantum state. Okay, it's associated with state. But here, what we are more interested in is the ability of a quantum mechanical operator like the S matrix to entangle. And then there's a subtlety here because the amount of entanglement generated by an operator actually depends on the initial state. Okay, the most commonly shown example, if you take a CNOT in the computational basis, then the CNOT acting on each of the basis vector give you another product state. But if CNOT act on this particular unentangled state, actually give you an entangled state. So that tells you that, the ability of an operator or a quantum gate to entangle depends on the initial state. And so that means to deal with this issue, what people have done is to define entanglement power essentially by averaging over the initial state. That is, you take your unitary operator, act on an arbitrary product state, then compute the entanglement of the outcome, and then average over the Bloch sphere of the two initial states. So then this becomes an averaging property that is associated with the quantum mechanical operator. Okay? And therefore, in this sense, the entanglement power is a measure of the ability of an operator to generate entanglement on product state. And so, but there is also another subtlety in this definition, meaning that the two operators, they would have the same entanglement power if they differ by single qubit operator on the left and on the right, because the way it's defined. Okay, so that introduces a notion of equivalent classes when two operators differ by single qubit operations. Okay, and then a minimally entangling operator by definition has zero entanglement power. So what does that mean? That means it's an operator that always takes a product state to a product state. Then entanglement power would vanish. So it turns out that if you ask a question for a two-qubit system, what are the all possible minimally entangling gates? It turns out that there are only two of them. First one is 1, the second one is swap, which interchanges the two qubit. And it's very easy to understand why these two gates, suppressors have zero entanglement power, because 1 always take a product state to product state, and swap also take a product state to product state. What is less obvious is that these are the only two. Okay? But you can prove that these are the only two minimally entangling states, and you can think of swap as -1 because swap square give you 1. And we can write the swap in terms of Pauli matrices, which is just 1 plus sigma dot sigma divided by 2. And this is a very useful identity as it turns out. Okay? So in what follow, what I'm going to do is that we know that S matrix is the unitary operator that takes an in state to an out state. So for a 2-to-2 scattering process, I'm going to think of the S matrix as a quantum logic gate acting on the two qubit system. So that means I'm really thinking about the 2-to-2 scattering in terms of a quantum circuit diagram here. Okay, then S matrix is just a quantum logic gate. And these two S matrices are in the same, have the same entanglement power if they differ by single qubit operation. All right? And so now let's consider the scattering 2 qubits in the low energy, and then only the S-wave channel dominates, and the S matrix, as I say, can be decomposed into the 2 channel, 1s0, 3s1. That means there are 2 scattering phases, delta 0 and delta 1, and then the S matrix is just written very simply in terms of the phase in the 1s0 times the spin projector into 1s0, plus the phase in the 3s1 channel times the spin projector into the triplet channel. right? This is just simple quantum mechanics. So what I'm going to do next is to use the identity here to rewrite the spin projector into one and swap. Okay? So when we do this, I'll rewrite both spin projector can be rewritten in terms of one and swap. Then you see that S matrix become this times 1 plus another coefficient times swap. Again, I'm trying to think of the S matrix as circuit diagram. So the first one is just two identity. The second one is the swap. Then from here, we can read off the conditions for the S matrix to be minimally entangling. That is, if I require the S matrix to be the identity gate, that means the coefficient of swap has to vanish. So that means delta 1 has to be the same as delta 0. On the other hand, if I require the S matrix to be swapped, that means coefficient of 1 has to be 0. That means the phase difference between delta 1 and delta 0 have to be pi over 2. It turns out if you translate these conditions into the effective Lagrangian, delta 0 equals delta 1 is precisely when you have SU4, SU16 spin flavor symmetry, whereas when the phase difference is pi over 2, it's precisely when you have a Schrodinger symmetry. And in both cases, you have entanglement suppressing S matrix. In the first case, it's identity. In the second case, it's the swap. Okay? And so we can extend this analysis to other spin 1-half baryons, which have a much richer theoretical structure and phenomenology. And because now I'm scattering, instead of just neutron and proton, I'm scattering the octet baryons. So that means I have 8 times A equals 64 scattering channels in total. That's obviously way too complicated. And therefore, it really helps to recall that strong interaction preserves charge and strangeness of the total system. So that means we can classify the scattering channel into sectors with definitive Q and S, and that also means the S matrix becomes block diagonal when you look at the individual distinct Q and S sector. And so that simplifies the whole analysis. Okay? So let me just give you the outcome of the analysis. So in the end, we're able to obtain the associated emergent symmetry when each Q and S sector is minimally entangled. Okay? And so what happens if we require, for example, these channels to suppress entanglement, we find SU6 spin flavor symmetry or conformal symmetry. If we require this subset to suppress entanglement, we find an SO8 flavor symmetry or conformal symmetry in the Lagrangian. And if we demand an even larger subset of channel to suppress entanglement, we find SU16 or SU8 in conformal symmetry. So every step of the way, by successively demanding more and more channels to minimize entanglement, we find larger and larger emergent symmetry in the effective Lagrangian. Okay, so that's the sort of what we learned in the case of a low energy QCD. And I promised that I will talk about the Higgs boson. So let me talk about the Higgs boson. Again, for this audience, I don't need to explain the great success of the Higgs. And also, I suspect everybody knows that measurement at the LHC point to a standard model like Higgs boson. Everything pretty much line up with standard model expectation. Okay? So it turns out that in most BSM model, a standard model Higgs is by no means generic. That means if I give you a 2 Higgs, any BSM model, you have to go to special corner parameter space in order to generate a standard model like Higgs. Okay, so it becomes a question, why, if we believe there's BSM model, then why do we observe such a standard model like 125 GeV Higgs? All right, so this is the most general scalar potential for 2 Higgs type of model, and again, I probably don't need to tell everybody that this is the prototypical model for BSM theories. And there is quote unquote a basis of these 2 Higgs doublets such that all parameters are real assuming it's a CP conserving two Higgs doublet model. And there are two VEV, V1 and V2, for each doublet, phi 1 and phi 2. Here, there are two Higgs doublets, so I'm referring to 1 and 2 here as the flavor index. There are two kind of flavor for the Higgs doublet. There is phi 1 and phi 2. And each one of them has its own VEV, and from the two VEV, we define this 10 beta, that is a ratio of V2 over V1. And moreover, there is a mixing angle in the CP even neutral sector that is defined as alpha. That is, you go from this flavor eigenstate to the mass eigenstate. There is a 2x2 rotation to take you from phi 1, phi 2 to big H and little h, which is the mass eigenstate. Then what does it mean to have a standard model like Higgs? A standard model like Higgs means that the cosine of beta minus alpha is much less than 1. And that's what we observe experimentally. But we don't know why. Why we have to be in this special corner that cosine of beta minus alpha is much less than 1. And moreover, just some terminology in the literature, this limit is referred to as the alignment limit. And this is more general than the decoupling limit when you take all the heavy Higgses to be very heavy. So the alignment, there could be cases where the extra Higgs boson are not heavy, but you have a 125 GeV Higgs boson that is completely standard model-like. And that is the alignment limit. So as I say, experimental data point to an approximate alignment limit. And so what we did is the following. We studied the tree-level S matrix in the limit that gauge and Yukawa couplings are turned off. So we look at the 2-to-2 scattering of Higgs boson. The phi A and phi B here refer to the flavor index. As I said, there are two flavors. So you can think of this as a scattering of 2 qubits, because A and B can be 1 or 2. Okay, so it's a two-state system. And so these are the Feynman diagrams for these 2-to-2 scattering of Higgs bosons. And moreover, I want to emphasize that we want to look at the S matrix instead of just the T matrix, because the T matrix is related to the usual scattering amplitude we compute. However, T matrix itself is not unitary. And I want to have something that is unitary so that I can interpret it as a quantum logic case. So that's why all the entanglement suppression condition that what I would impose is imposed on S, not on T. Okay? So I'm going to demand that the S matrix is in the equivalent class of identity gate in the flavor subspace. From here, I can derive the following conditions on the tree-level amplitudes. It's a bit tedious, but in the end, it's straightforward to do it. And these are the conditions. Now the question is, what kind of scalar potential could give us such tree-level scattering amplitude in such a way that the S matrix is the identity gate? Okay, what scalar potential could give us such an entanglement suppression in the S matrix? It turns out that the scalar potential is very simple. It just looks like phi 1 dagger plus phi 1 dagger phi 1 plus phi 2 dagger phi 2 plus whole thing squared. And there are 8 real degrees of freedom. If I collect all the real degree of freedom into an 8-dimensional vector, the potential just looks like phi dot phi plus phi dot phi whole thing squared. And that makes it clear that this potential has a maximum SOA symmetry, which rotates the A real component into 2 complex doublets. And the SOA is broken down to SO7 by the Higgs VEV. And in this case, all non-standard model Higgs are ghost-stones because I turn off gauge couplings and Yukawas. But once I turn on gauge coupling and Yukawas, they become massive. And moreover, a natural outcome of this scalar potential that I get a standard model Higgs boson that is the 125 GeV Higgs. In this sense, a standard model like Higgs is a consequence of entanglement suppression. Okay? So my time is up. Let me just give you the outlook. I hope it's clear that we are in pursuit of a new paradigm here. That is, can symmetry be the outgrowth of more net fundamental principles? And the answer appears to be a tantalizing yes. Because what we are doing is that we are trying to relate entanglement suppression with emergent symmetry. But with the benefit of hindsight, it's probably not that surprising that these two are related. Why is that? Because we quantify entanglement using von Neumann entropy. So when entanglement is minimized, meaning that the entropy is minimized. And the intuition is that when entropy is minimized, it tells us that there is some kind of order in the system. Okay? On the other hand, the concept of symmetry is also telling us there is some kind of order in the system. So both concepts relate to the presence of order in our system, intuitive. However, I think what's striking is that this is the first time we have the predictive power, meaning that I can tell you if you minimize this much entanglement, I get this much symmetry, and vice versa. Okay? And so there are lots of other questions we can pursue, but I would just stop here.
Thanks, Jan, for the nice talk. Question, comments? No questions, no comments. Well, I have one myself. Have you thought about doing four, more general than a two Higgs doublet model, like a heft or something? Like this, Higgs effect field theory that you have way more parameters.
What is the question? Sorry.
If you don't do it for a two Higgs doublet model, but something like heft that has more parameters.
If you don't do two Higgs, but then what do you do?
Like a more general description of higher Higgs or.
So you mean more Higgs doublets? You mean?
Yeah.
So like three Higgs doublets?
Yeah, or something more general.
We have not looked at three Higgs doublets or four Higgs doublets. Right.
Yeah.
Anyway, okay. I think to me, two Higgs doublet model is hypothetical enough.
One question. I think that these kind of models, you have to extend the content typically with more fermions just to have a phenomenologically acceptable model.
Indeed. So that's why I say we are doing the 2-to-2 scattering amplitude. We're doing the calculation in the limit gauge couplings and Yukawa couplings are turned off. And in that limit, as I said, there are many massless ghost zones. And so to have a realistic spectrum, we need to turn on the gauge coupling. We need to turn on the Yukawa couplings to have a realistic spectrum.
And at the end of the day, you have to break probably softly the global symmetry that you have.
Yes, exactly.
So since you are breaking that symmetry in an explicit way, in that way, is there any consequence for entanglement? So is there something that is preserved with good properties of so breaking translate into some kind of...
excellent question. It's something we are looking at right now.
Thank you very much for the nice talk. So you mentioned that to suppress entanglement, the scalar potential has maximal SO8 symmetry, and then you said follows from this scalar potential.
Yes.
What does that mean?
Meaning that if you start with a scalar potential like this, if you start with a scalar potential like this, there are only two parameters, y and lambda.
Yes.
Okay? And you break the valve. You give one of the Higgses a valve. And then you look at the Higgs that carries the valve. That Higgs is also the mass eigenstate.
So the
In general, okay, in the general 2x doublet model, when you have these two flavor eigenstates, when phi 1 gets a VEV, phi 2 gets a VEV, okay? Another way of saying having a standard model like Higgs, meaning that the 125 GeV Higgs, if it carries a full VEV, then its property will be standard model-like. So that means if the Higgs that carries the full VEV is also the mass eigenstate, then we have a 125 GeV Higgs. So that means, and so this statement here is that if you start with this scalar potential and you work out the detail, then you will see that the Higgs that carries the full VEV is also the mass eigenstate, whereas in general, it's not the case.
Okay, thank you.
Thank you very much. It's very interesting. Okay. In the world of quantum simulations, there's some groups of people who are trying to work out how to more efficiently perform classical simulations of quantum systems. And for some of those studies, I think they've been looking at which Lie groups they can use to try and reduce the problem down to more simpler problems, which can be efficiently classically simulated. Right. It feels, and they've got a variety of formal results in it, it feels like there should be some connection between the sorts of things they're doing from that side and the sorts of things that you're doing.
So the way I would phrase it is that in the end of the day, it's really a question like this. What is the information theoretic measure to quantify the amount of symmetry in a physical system? And once we know this, I think it would definitely help us devise more efficient quantum algorithm to simulate physical system with symmetries. In one typical example, I show that Schrodinger symmetry is associated with the swap gate. So that tells us right away, if we want to quantum simulate a system with Schrodinger symmetry, I need to put in the swap gate, at least in the spin subspace. So definitely, I think they should be very interesting interplay in the long run in terms of how this kind of knowledge, how it can help us to devise more efficient quantum algorithm.
Any more questions? Then I think we can thank Jan again.